Hi everybody, today we have the last of our series of videos about zeros of polynomials. And this video specifically deals with complex zeros. Sometimes graphs may not touch the x-axis, or might turn at places that are unexpected. These functions often contain complex zeros. What that means is there are zeros, but they're kind of hidden from sight. So what we want to do is take a closer look at the function to see how we could find these values. So as a quick reminder, a complex number can be written in the form a plus bi, where a and b are real numbers. This means that all real numbers are complex numbers where the b is equal to 0. So we're going to look at the fundamental theorem of algebra. Every polynomial equation of degree n has n roots in the complex number field. It's important to say that the n roots don't have to be unique. Remember, we have multiplicity, so we can have a repeated root, and because real numbers are complex numbers, some of the solutions or all of the solutions could be real numbers instead of imaginary. Related to this, we have the complex conjugate theorem, which says if a plus bi is a root of a polynomial function, f of x, then a minus bi is also a root of f of x, and that works both ways. Let's find the conjugate of each complex number. So if I have 2 minus 3i, the complex conjugate is 2 plus 3i. So I'm just changing the sign between the real and imaginary part. 5 plus 6i would be 5 minus 6i. If I just have 7i, then I make it negative 7i, or negative 9i becomes positive 9i. The sign that is changing goes along with the b term, not with the a. So if I'm missing the a term, that's okay. I just put a negative in front of whatever I had for the b. So now we're ready to find all solutions to a function. So here I have f of x is 9x cubed minus 21x squared minus 15x minus 9. I'm going to start the same way I have been. I look at p as my last term. I look at q as my beginning term. The factors of p are plus or minus 1, plus or minus 3, plus or minus 9. My factors of q are plus or minus 1, plus or minus 3, plus or minus 9. When I form p over q, I have plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1 over 3. Remember, 3 over 3 is 1. I don't need to use it. 9 over 3 is 3. I already have it. Don't need to say it again. Let's divide by 9. I have plus or minus 1 over 9. If I do 3 over 9, I get 1/3. If I do 9 over 9, I just get 1. So these are all of the numbers I want to plug into f of x to see if I have any rational zeros. So let's put that into the TI calculator. So I'm going to put the values I have from my rational roots. I had 1, negative 1, I had 3, I had negative 3, I have 9, and I have negative 9. So with the integer values, I can see that when x is equal to 3, I do have one solution. So we had a couple of fractions. So I had 1/3, negative 1/3, I had 1/9, and I had negative 1/9. The only thing I'm taking back is the x equals 3. So I'm back to my function. I know x is equal to 3, so I'm set up to do synthetic. I'm going to put 9, negative 21, negative 15, negative 9. I'm bringing the 9 down. 3 times 9 gives me 27. When I add that to negative 21, I get 6. 3 times 6 gives me 18. When I add that to negative 15, I get 3. 3 times 3 is 9. I get 0. What I'm left with is 9x squared plus 6x plus 3. I want to find the zeros of this. I noticed that 9, 6, and 3, I could take a 3 out. Then I have 3x squared plus 2x plus 1. You could try doing the AC method. 3 times 1 is 3. I'm not going to find any positive factors of 3 that add up to 2, which means I have to do the quadratic formula. So x will be negative 2 plus or minus the square root. I have 2 squared minus 4 times 3 times 1 all over 2 times 3. I can simplify that to negative 2 plus or minus the square root of 4 minus 12 over 6. That gives me negative 2 plus or minus. When I do 4 minus 12, I get negative 8 under the square root over 6. This is negative 2 plus or minus. Let's say that negative 8 is 4 times 2, and let's take that negative 1 outside as an I, still over 6. Square root of 4 is 2, so I have negative 2 plus or minus 2 square root of 2, I over 6. Since everything is a multiple of 2, I can divide 2 into each of them. So this gives me a 1, this gives me a 1, and in the denominator I get a 3. I'll write it over on the left. X is equal to negative 1 plus or minus the square root of 2i over 3. So here I have 3 solutions. I have 3, I have negative 1 plus or minus the square root of 2i over 3. Let's do that again. I think practice really helps. So here I have x cubed minus 5x squared plus x minus 5. Now this one, when I first look at it, I do kind of notice that it goes x5, x5. That makes me think maybe I could factor by grouping here. The first 2 terms have an x squared in common. I'm going to take it out. It gives me x minus 5. The second 2 terms, when you look at x and 5, and you're like, they don't have anything in common, you can always factor out a 1. We want to do that, so I have x minus 5 as a factor. X minus 5 says I have x minus 5 times x squared plus 1. I'm going to set that equal to 0. The first term, x minus 5, says x equals 5. The second term, x squared plus 1 being 0, says x squared is negative 1. When I take the square root, I get x is plus or minus I. So anything that's a negative under the radical comes out to be an I. So here I found the zeros. I have 5, I have negative I. On the next page, I just want to write this in factored form. So remember, we had 5, we had I, we had negative I. So this is x minus 5, x minus I, and x plus I. So even with the factoring of complex numbers, we do it the same way we do it when we get a real number. A little bit bigger, or actually a lot bigger, I have 3x to the 5th plus 2x to the 4th plus 105x cubed plus 70x squared minus 108x minus 72. Now you've seen me do this before where it gets really big, that I say, let's just head over to Desmos and see if we can get a little clue as to how to start this one. We could, of course, do rational roots. That's going to be really long. So instead, I'm going to see if I can see any intercepts to get me started. So I plugged in my function 3x to the 5th plus 2x to the 4th plus 105x cubed plus 70x squared minus 108x minus 72, and immediately I can see 3 zeros, negative 1, this negative 0.67, and here add 1. Notice each of them crosses, so I'm not expecting a multiplicity to come out there at all. This negative 0.667 would be negative 2/3. So I have negative 1, positive 1, and negative 2/3. We're going to do synthetic 3 times. So I'm going to start with the negative 1. I have 3, 2, 105, 70, negative 108, negative 72. 3 comes down, I get negative 3. When I add, I get negative 1. Times negative 1 is 1, I get 106. Which when I multiply gives me negative 106. I subtract, I get negative 36, which becomes positive 36. When I add negative 108 and 36, I get negative 72. Negative 1 times negative 72 is positive 72. I add to get 0. I've used the negative 1. Let's go on to the positive 1. Bring the 3 down. Multiply by 1, I get 3. That gives me 2. 2 times 1 is 2. I get 108. I add 108. That gives me positive 72. Times 1 is still 72. There's another 0. One more number, negative 2/3. 3 comes down. Times negative 2/3 is negative 2. That gives me 0. 0 times negative 2/3 is still 0, which is 108. Negative 2/3 times 108 gives me a negative 72, which gives me 0. Watch what happened. I started at power 5. The first time through, took me to power 4. Second time, took me power 3. And my final one gave me x squared. So this stands for 3x squared, 0x, plus 108 is 0. If I take the 3x squared plus 108 equals 0, I can move the 108 to the right and then divide by 3. Negative 108 over 3 says x squared is negative 36. I take the square root of each side, and that says x is plus or minus 6i. So notice I'm getting the number and its conjugate all at once. So what did we have before? We had 1, we had negative 1, we had negative 2/3, we have 6i, and we have negative 6i. So we have 5 solutions to this power 5 polynomial. If we wanted to write that in factored form, you would want to pay attention to this negative 2/3. We've said before that sometimes the fractions become a problem. I have x minus 1, x plus 1, x plus 2/3, x minus 6i, x plus 6i. But quickly look back and see we have that 3 that was our coefficient. So we would want to multiply a 3, distribute it through to get x minus 1, x plus 1, 3x plus 2, x minus 6i, and x plus 6i. So I know, lots of steps, but very doable steps. Make sure you're using the technology to help out, but I really like that this is consistent, whether we're using real solutions or complex solutions. We're kind of doing the same steps all along. Hope that helps. Good luck.